We are next going to talk about corners as a motivator for the simplex algorithm, which is how you're actually going to solve linear programs by hand, and which is actually how computers solve linear programs in many software applications. So what I want to begin with is relating the idea of a corner as a geometric concept with an algebraic concept. And what do I mean by this? You can think of things this way. When we talked about the graphical method, okay, when you learn the graphical method and you solve the linear program in 2 dimensions using that approach, we started with the assumption that the feasible region was a bunch of inequalities. It was a bunch of expressions like this, right? AI transpose x less than or equal to bi. So let's just write an example here. Let's say x1 plus 2x2 is less than or equal to 4. I'll just give myself a couple. That seems like a nice one. And then I'll do a 3x1 plus 2x2 less than or equal to something nice and even 6. Okay, and you'd have a whole bunch more of these, but I'll just stick with 2 for now. Okay, you had a bunch of inequality constraints like this, and I've got the inequality going the same way here for both of them for no particular reason. And so we could say, all right, those 2 inequalities define a corner, right? And in what sense do they do that? What is the algebraic notion here? So let's draw some axes like that, an x-axis and a y-axis. And I'll give myself some tick marks. And let's draw these 2 constraints, and then let's draw the corner that comes from them and use this to reason about things. So this first one here, x1 plus 2x2 less than or equal to 4, that looks like you'd have a that line looks like this here. And of course you're below that line as you probably know by now. So we'll do that. And then the next one, 3x1 plus 2x2 less than or equal to 6, that's this line here. It looks like that, and you're under this thing. And so we look at these 2 constraints put together, and we'd say they define a corner, right? It's this thing right here. And it's where, if I shade this in a lot, I hope this shows up okay. But you know, the corner is, it's where those two inequalities intersect. And what it actually means here, right, is how do I calculate that corner? Well, it's not so much that the inequalities intersect; it's that you would actually take these 2 inequalities, these 2 constraints, and you would set them to be equal signs, and you would solve for the intersection of those 2 lines, right? So this, let me draw an arrow like that. This corner over here would be obtained by solving the equations x1 plus 2x2 is equal to 4, and 3x1 plus 2x2 would be equal to 6, right? You would solve this equation, and you would recover this corner here, right? Now, why is it that we can solve for this? It's because we're in 2 dimensions, because we're drawing it on a piece of paper, and we have 2 variables, and so you can solve systems of variables with 2 equations, 2 unknowns, right? So corners in 2 dimensions are obtained by like taking 2 lines and intersecting them, which effectively gives you 2 equations, 2 unknowns, 2 linear equations that you're solving. Okay, in 3 dimensions, all right, yeah, I've got a picture of it over here, this polyhedron that I've sketched there, and you can see these various corners that I've identified, but these corners here are actually defined as being the intersection of three equations, right? Let me erase some of this stuff here, and let's look carefully at this polyhedron. The corner, let's say this corner right here, this corner, as you can see, it is the intersection of 3, whereas we had, let me try some visual aids here. In 2 dimensions, we drew these lines, right, and we had to be below the line. in 3 dimensions, you have planes going through 3 dimensions, and so I'll do that with like playing cards. And a corner would be like the place where the 3 planes kind of intersect like that, right? That's how that works. And so what I want to indicate here in this diagram is that corner there constitutes the intersection of this plane here, which is that face, and the plane that governs this thing, and the plane that governs this thing. Okay, so all I want to get at here is that the way you talk about a corner of a feasible region for the moment would be that you isolate a certain set of the constraints, of the inequality constraints, and you write them as equal signs, and then you solve for those variables. So when you have 2 variables, the sides, or the corners rather, are intersections of 2 constraints, and then in 3 dimensions it would be intersections of 3 constraints. In 4 dimensions, if I were able to draw that, it would be intersections of 4 constraints, and so on and so forth. So I want to begin by identifying that, because that's going to be important for where we're headed. Let's suppose, and I have had students that felt this way, when you go through the graphical method, right, there's this step in the end. Let's say I've got my I've got my feasible region here. And then what did you do in the graphical method? You drew a bunch of level sets, and you looked for the one where, or you drew your objective function vector, right? And then you drew your level sets, which were the lines perpendicular to that objective function vector, and then you picked the corner as being the optimal solution was the corner where you were like just barely intersecting that feasible region, right? Now, I have had students say, I really hate that step. I've had students who complain and said, I really don't like this whole level set business. It's too frustrating. It's too confusing. Could I instead just write all the corners and choose my favorite one, or choose the best one? So the idea was like this. The idea was, could you say, well, okay, I'm just going to do this. Let's say my feasible region looks like this thing, right? Is it enough if I just said, well, I know based on the previous discussion that we've had that the solution has to be at a corner, assuming the problem is feasible. So is it okay if I just look at every single corner and evaluate the objective function there, and then just see whichever one has the best objective value, right? If it's a minimized problem, the smallest, then maximize would be the biggest. The answer is yeah, you could totally do that. That's a perfectly valid way to solve the problem. It's perfectly valid. The exceptions to that are kind of silly. They're sort of pathological. They don't generally cause issues for you, but I'll explain them now. And the first one is that, well, maybe you have an infeasible problem, right? Maybe this maybe this feasible region doesn't actually exist because you've eliminated all possible points. If you have an infeasible problem, which would mean like you have 2 constraints that are incompatible, so x1 plus x2 is less than or equal to 1, and x1 plus x2 greater than or equal to 2, right? You can't simultaneously satisfy those, so you can't even draw the feasible region, right? There's no feasible region, and therefore, of course, there's no corners, so the concept doesn't make sense. You could have an unbounded problem too, right? Maybe your problem is unbounded, so again, it doesn't have a solution because you can make the objective value as good, as favorable to yourself as you'd like it to be. And I've got an example of this here. Maximize x1 plus x2 with x1 plus x2 greater than or equal to 1, and both variables are non-negative, right? It's easy to verify if you try to run the graphical method on that you can't solve that, because you can make the objective function as big as you would like it to be. The only other exception, and this is one you're not going to see, would be if you could have a feasible problem, you could have a bounded objective value, but maybe your feasible region doesn't have any corners. Okay, and this example here illustrates that. Maximize x1 plus x2 subject to x1 plus x2 less than or equal to 3. Right? The maximum objective value of that is obviously 3 because the constraint that you have is the same as the objective value, right? Maximize x1 plus x2, but x1 plus x2 has to be less than or equal to 3. Well, okay, 3 is clearly the optimal solution, but the feasible region doesn't have any corners, so you couldn't possibly enumerate them. But these are all sort of tautological cases, right? These are things where you'd kind of, if this situation were arising, you would probably identify it by some other means. So you don't generally need to worry about such things. Again, the central premise here that I want to get at is just that it would be perfectly valid. It is a perfectly valid means of solution to simply say, I'm going to look at every single corner of my feasible region and I'm going to choose the best one. It is perfectly valid. The problem with that is that it does not scale very well. It doesn't scale well because you might have to check all, if you have m constraints, then the number of constraints that you would have to check would be m choose 2 in 2 dimensions. And these number could be quite a bit higher in higher dimensions. So let me give an example of that, of the scalability, because I want to emphasize that point more clearly than I just did. Let's take this system of inequalities here. Okay, maximization, you've got, whatever, some objective value, who cares? And here I have, let's see, 1, 2, 3, 4, 5, 6. I have 7 constraints, and I have 4 variables. And let's suppose I said to you, okay, I want you to solve this linear program. And you said, okay, well, I know that it is a valid solution method to just enumerate all the corners, as we just saw a moment ago, and choose the best one of those. So maybe I'll do that. So for this setup here, we have 4 variables, which means that we have to look at sets of 4 constraints at a time. Right, go back to my geometric discussion before. Remember, as I said, when we did 2-dimensional problems, I said that what you would do is you would look at you would look at pairs of constraints, right, like these two over here, and you would look at where they intersected, and you would look at that, you would solve for those variables. And then in 3 dimensions, as I have in this picture over here, what you would end up doing is solving for 3 variables with 3 constraints. And for this example here, with that matrix that I just drew, okay, this is 7 constraints and 4 variables, so I would have to look at sets of 4 constraints and solve for them. So what does that mean? It means I'd have to look at 1, 2, 3, and 4. I'd have to solve this system of equations here. It would be, I don't want to copy the whole thing out, but I do want to get the point across. I would have to solve 4x1 plus 9x2 plus 4x1 plus 7x4 is equal to 25. And the next one there, 6x1 plus 5x2 plus 9x3 plus 10x4 is equal to 20, what's the number there? 31. And you would do the same for these other two as well. The other left-hand side would be 20, and the other left-hand side would be 21. And you'd say, okay, is that a corner or is it not? You'd solve this system of equations with those terms in there. And I go, okay, that's me checking if the first 4 constraints define a valid corner. And then I would check for I would do, okay, the first 3 constraints plus the 5th constraint. And I would solve for that. And I'd ask, does that form a valid corner or not? And I would iterate through this process. I would look at every set of 4 constraints from that set of 7. And I would ask, does this form a valid corner or not? And that's a lot, right? What is the number here in this case? In this case, that number turns out to be, if you remember from probability, this is 7 choose 4. That's the number of ways I could take 7 distinct objects and choose 4 of them. So If you're in 331, we've already talked about this, but I'll do an example with, like, I've got a bunch of playing cards here, and I've got 7 playing cards, and so this number that I've written here, 7 choose 4, that's the number of ways that I could take 4 elements out of that set of 7, the number of possible sets of 4 that I could select out of this set. Okay, and that's a pretty big number. And in fact, it's actually not that big. It's only 35, but you can imagine. You can trust me. I think that this number does not scale very well. So, if the proposed solution for solving linear programs was simply write out all of the corners and choose the one that is best, it would take you a long time to do that. Now, before I get into the general algebraic method for identifying corners, I do want to make sure it's clear why certain subsets of constraints give you a corner and others do not. And I think the best way to do that is to go back into 2 dimensions one last time. So this is we'll look at this linear program here as if you were running the graphical method on this. It's got 5 constraints. It has 2 variables in it. And if we look at the diagram here, you can see that the number of corners is 1, 2, 3, 4, 5. So there are 5 corners that we can look at in this diagram here. And now let's suppose I asked you, okay, I'd say, okay, write down what those corners were. And you'd say, well, okay, those corners are, I get them by looking at every pair of constraints, right? I look at every pair of constraints, I intersect them, and that could give me a corner. But then you'd look at this diagram and you'd say, or this set of inequalities, and you'd say, well, wait a minute, there's actually 10 different pairs, right? Because I could go 1 and 2, I could go, this is going to take a long time if I use my pen this way. I could do 1 and 2, I could do 1 and 3, I could do 1 and, here's what I'll do. I could do 1 and 2, I could solve for 1 and 3, I could do 1 and 4, I could do 1 and 5, maybe move over here, I could do 2 and 3, I could do 2 and 4, I could do 2 and 5, I could do 3 and 4, and 3 and 5, or I could do 4 and 5. Right? That's how many pairs of constraints I could look at in isolation. And there's 10 different pairs. So how could it be that there's 10 different pairs of constraints here, so therefore 10 potential corners, but based on that picture we just looked at, in fact, there's actually only 5. What are those missing corners, or where do they go? And the answer becomes clear if you look at the diagram again. So let's draw that. Let's look at the feasible region, and let's look at the pairs of constraints that aren't corners. Okay. In fact, let's do this. I'm going to pick a constraint that I happen to know does not give me a valid corner, and that one is the constraint that says x2 is less than or equal to 3, and the constraint that says 6x1 minus 4x2 is less than or equal to 0. Okay, so constraint 2 and constraint 3. Let's draw those constraints. That's this constraint here, that's constraint 2, and this one here is constraint 3, like that. And so where do they intersect? If I wanted to solve for for the corner that they produced, it would be this one. But this is not a corner of the feasible region. It's not a corner of the feasible region because it violates this constraint here. This is the constraint that says that x1 is 5x1 is less than or equal to 6. That's the third constraint over here. 5x1 is less than or equal to 6, and therefore this proposed corner, which I produced by solving for the second and third constraints to hold with equality, and to look at that one, I'd say that isn't a corner because it violates this constraint over here. All right, and in fact, that's true for all of these other proposed constraints. So there's this one, there's this one down here. This also is not a valid corner because it violates this constraint. If you look at this constraint there and this one, you can see there's some prospective corner way off here, which is not feasible because it violates, for example, this constraint. And then there's another one way down, like south of this picture somewhere. Okay, so that's the idea. So you've got all these, in 2 dimensions, you have pairs of constraints, and you're looking at pairs of them, and you're asking, does this form a corner or not? So what you do is you solve for the intersection of those constraints. That's just linear algebra. And then you have to ask, is this proposed corner, is this solution I get, is it actually feasible? Does it satisfy the other constraints? As you can see in this diagram that I just drew, the answer is often no. And that's how you end up with 5 constraints with 10 possible corners that you'd have to check. But in fact, in this diagram, there's actually only 5. So let's extend this logic out and do it in just algebra without doing diagrams, and just see how this process works. I'm going to explain the process here. I'm going to state it in words, the algorithm for computing corners, and then I'm going to work through an example here. So this is when you have a set of constraints that is expressed only with inequalities. Okay, notice I've had to make this assumption throughout that all of the constraints have of inequality form only. We're going to look at the standard form case next, but we'll start with this one. When all my constraints are linear inequalities, and you have to find all the corners of that feasible region, this is how you would do that. For notational purposes, we'll say M is the number of constraints, so the number of rows there, and N is the number of variables. What you do is you look at every set of constraints of size N, and for each such set, which we'll call S, what do? Number 1, or step A, you convert those inequalities into equal signs. Step B, you solve for those constraints, which you can do because you have n equations and you have n variables, and you obtain a solution X. And when I say solve, you do it using, MATLAB, Python, Wolfram Alpha, whatever you like. In principle, behind all of this, you'd be using Gaussian elimination, but this is not a linear algebra course, so you don't need to worry about that. And then the third step, so now you've got a point X, you've got a solution to these linear equations, and you just ask the question, does this point that I've solved satisfy the other constraints? And if the answer is yes, then you have a corner, and if you do not satisfy those constraints, then you do not have a corner. Let's do an example in 3 variables. So now I've got 3 variables and 5 inequalities, 5 constraints, and you have to find all of the corners of this thing over here. So we'll ask, how many sets of constraints do I have to check? I've got 3 variables, I've got 5 constraints, so I want to look at all the ways of selecting 3 constraints out of these 5. And I've written them over here. There's 1, 2, 3, 1, 2, 4. What a strange way of numbering these things. I'm missing at 1, 3, 5. That's over here. I don't know why that happened. 1, 2, 3, 1, 2, 4, 1, 3, 4, 2, 3, 4, 1, 2, 5, 2, 3, 5, 1, 4, 5, 2, 4, 5, and 3, 4, 5. Okay, that's 10 possibilities. So there's 10 combinations of these constraints that I have to look at. So I'll run through a few of these. I won't do all 10 because you'll get bored, but I'm going to do just enough that I hope the pattern becomes clear. So we'll try just the first 3. We'll say, okay, let's try constraints 1, constraint 2, and constraint 3. Go back to that original system here, and you can see that that means we would take these 3 constraints here like that. And step 1 would be we take these inequalities and turn them into equal signs. Okay, so turn those into equal signs and solve for x1, x2, and x3. Okay, that's what I've done here. You get those constraints, write these as inequalities, and solve them, and that gives me this expression here, minus 15, 1, 13. That's the solution. And we just ask, okay, that's that's what we would get if we solved by setting the first 3 constraints to be equal. And we've ignored completely constraints 4 and 5, right? We solved for by taking the first 3 constraints, we ignored 4 and 5, constraints 4 and 5. And so now we go back and we check. We say, does is constraint 4 satisfied? Constraint 4 says 5x1 plus 5x2 is less than or equal to 4. That one's fine, but constraint number 5 is not. Constraint number 5 says minus x1 plus 5x2 minus x3 less than or equal to 2. That is not satisfied. So we violate that fifth constraint, and therefore we do not have a corner. So isolating the first three constraints does not give us a valid corner. The next one we're going to do is constraints 1, 2, and 4, I believe. Let me check. I'll clear that off, and now I want to make sure this is 1, 2, and 4 that we're doing next. Yeah, 1, 2, and 4. So 1, 2, and 4 means you would isolate these two. This is 1 and 2, and then constraint number 4, like that. And once again, you would set all these inequalities to equal signs, as we'll do here. They set those to be equal signs, and then you would solve for these variables, and that gets you this system here. And then again, so we've solved for 1, 2, and 4, and we've ignored 3 and 5. So we'd want to check, is 3 satisfied, and then is 5 satisfied? Well, 3 is not satisfied. You can just plug these numbers in there and find that it's violated. So you'd say, nope, again, not a corner. We'll do another example here. 1, 3, and 4. 1, 3, and 4 again turns out to not be satisfied. And so what would I do there? 1, 3, and 4 means you would take the first, third, and fourth constraints. I'll just go back to make sure this is... if it feels like I'm repeating myself a lot and you're getting bored, that's a good thing. It means you kind of know what I'm about to do next, and this is not exciting. That says you take constraint 1, and then you ignore 2, and you look at 3 and 4, and you solve for the system of equations there. Okay, so you solve for that, and you get this solution here. So we solve for 1, 3, and 4, and we were ignoring 2 and 5, therefore. And when you plug in 2 and 5, you find that constraint 5 is not satisfied. So that's 3 potential corners that we've looked at, and we've ruled out those 3. We've said, nope, none of these 3 was a corner. And remember, there were 10 total that I had to check, 10 sets of 3 that I had to check. So these do not work, but the next one does, 2, 3, 4. That's the second, third, and fourth constraint. You solve that system as I did there, and indeed these constraints are satisfied. So I'd say, hey, I've got a corner now. This is a corner, 0.505, 0.295, and 0.314. That's a valid corner, okay? So at this point in time, I've ruled out 3 out of the 10 potential corners because I found 3 cases where the constraints were not satisfied, and I've identified 1 as I just did now. There are 6 remaining corners that I have to check, and it turns out that there are 2 remaining corners, which is 2, 3, 5, and 3, 4, 5. So I've now got, I mean, I would just do the algebra there. It's boring, but if I were to just run through that, you'd find that there were 2 remaining corners, so 3 corners total. Here's some MATLAB code for computing the corners in MATLAB in the inequality version. We'll do a demo of this in class so you can see it, but the source code is there for your reference. If you believe what I've done so far, if you're okay with it, then we're already probably about a third of the way towards understanding the simplex method, which is the goal of this lecture. The next step is I'm going to mention something aside that we'll refer back to later, which I call the global property of corners. And it is the following fact. It is that if you have 2 corner points, well, first we'll do a definition. 2 corner points, you say they are neighbors if the constraints that define them are all the same, except they differ by exactly 1. And let me pull up that picture of the polyhedron to illustrate that. We'll do this in 3 dimensions. It's a little more interesting. Ignore this red thing here for now. That's not important. Disregard the red, and we're going to look at these 2 corners, which I'll sketch here. We will do, I'll get rid of the red completely, so I'll look at this corner here, and I will look at this corner. Okay, you see these 2 corners, and we can look at them with our eyeballs, and we can say, yeah, these corners are clearly next to each other. in some sense, right? They're connected by this line segment here. So yeah, they're neighbors of each other in some visual sense. Let's define what we mean by that mathematically. These two corners, I say that they are neighbors. And the reason I would say that here is if I mark, I hope this shows up okay. I'm going to mark this corner, this face here, sorry. This constraint I'll mark with a letter A. I'll mark this one with a letter B. I'll mark this one with a letter C. And this little triangle down here, I'm going to mark with a letter D. And I hope that shows up. Okay, I've got A, B, C, and D. And we'll look at this corner here. And we'll say this corner, we can look at that and we can say this corner is where A, B, and C all intersect, right? It's the intersection of A, B, and C. It's where those three constraints, the constraint for A, constraint for B, constraint for C, it's where those three constraints all kind of are aligned with each other. Whereas this constraint here at the bottom is the intersection of B and C and D. So both of these two corners have B and C in common, and they differ just by 1, right? They differ because, let me just write this really quick. I've got one corner which is A, B, and C, and I've got another corner which is B, C, and D, and both of them have B and C in common, and then you just replace the A with a D. And so that algebraically is how we would say two corners are neighbors of each other in the sense that it's sort of confirmed visually by this diagram. I'll draw a picture here too in 2 dimensions to illustrate this as well. I think maybe the 2-dimensional case is a bit easier. We would look at, let's say, and now I know I used Roman numerals before, but I'll stick with the letters here. So I'll call this one A, B, C, D, and E. And we can say, okay, for this corner here at the top, who are the neighbors of it? Well, obviously it's this one and that one. And indeed, the corner at the top is A and B. That's where A and B intersect each other. The corner here at the left, that's where B and C intersect. And this corner here on the right is where A and E intersect. And you can see that, okay, so A and B intersects with A and E. They both share an A. And A and B intersects with B and C because they both share a B. Okay, so when we talk about corners being neighbors, what we mean is that the constraints that define them, the constraints that we had to choose to, identify that corner, the set of constraints that satisfies, that defines these corners differs only by 1. So that's what that means when we talk about neighbors. That's going to be the key concept that underlies the simplex method. So I was talking about this global property of corners, and what do I mean by that? The global property of corners says the following about a linear function and corners on a polyhedron. It says that if a corner point has an objective value that is not worse than its neighboring corners, then it is optimal. Okay, my thesis advisor used to say that if, it means that if your lawn is nicer than your neighbor's lawns, then you must have the nicest lawn on the whole block. Okay, so if you're at a corner and you evaluate the objective, this linear objective value at that corner, you say, okay, the objective value here is, 23, and you look at your neighbors. You don't look at all the corners, you just look at your neighbors. If your objective value is at least as good as all your neighbors, in other words, if none of your neighbors is better than you, then you put your pencil down, you say, I'm done, I've solved the problem. Okay, this turns out to be really, really important. Why? Because if we didn't know this fact, then the only way we'd be able to verify if a corner was an optimal one is by looking at all the other corners. And as we've just seen, there might be a lot of corners you have to deal with. So this result tells you that you don't have to look at all the corners of this feasible region. In fact, you only have to look at your neighbors. So what this tells you is this gives you a pretty quick way of shortcutting, at least in a visual sense, of how to solve problems, say, in the graphical method. Okay, let's take, this is the same feasible region here that we had in the very first problem when we talked about the graphical method. But now we'll do In fact, we'll keep the same objective value too. Maximize 5x1 plus 4x2. And what we're going to do here is we'll apply what's called the, well, we're actually going to do this with the simplex method here, but I'm going to do it just sort of visually, and that method is this. I skipped right over this. Step one is you start at any corner of the feasible region. Okay, how do you actually find a corner to start with? We will get into that. Pretend it's been given to you. Okay, start with any corner of the feasible region, and you ask, are any of your neighbors better than you? Okay, if not, then you're done, because we just stated this fact about the global property of corners. So if the answer is no, if you're as good as all your neighbors, then you put down your pencil, you say, I'm finished. Let's suppose the answer is yes. You go, oh yeah, that corner is better than me. Then what should you do? You should move to that corner and then look at your neighbors from there. And you keep doing this, what's happening? Your objective value is getting better and better, and at some point, you're going to finish and terminate, and you'll have found the optimal solution. Let's do a diagram of this in 2 dimensions so you can see what I mean. So we'll take the same linear program that we introduced the graphical method for. Step 1 of that procedure I just described said you start at a corner, and I'm going to say we'll start at this corner right here, 0, 0, which is, we're maximizing, so this is a pretty lousy corner to start at, but that's important for our purposes. That's helpful. So you'd say, who are my neighbors here? My neighbors are this corner up here upward, and then this corner over here to the right. And it's easy to verify that both of these corners are better than me. And so which one do I move to? I can move to either one, but I guess I'll pick this one here where you move to this corner here, like that. Okay? And now I'm here and I say, well, who are my corners? Well, there's this one, which I just came from, the origin. Obviously, that's worse than me because I just moved here. The other corner is this one, and that corner turns out to be better than me too. So then I'll move over there and say, oh, that corner's better. Okay, now I'm here. And now I look and I say, what are my corners, or what are my neighbors rather? Well, there's this one, and I've just come from there, so that one's worse than me. And there's this one here, and that one turns out to be worse as well. And so therefore, I've solved the problem by only looking at, in this case, there were 3 corners I ever touched. I started here in the origin, then I moved to the right, and then I moved northwest, and then I put down my pencil and I'm done. Okay, now that I've described that process, maybe the red path that was in this picture a moment ago that I skipped over might be more relevant. It's the same idea. You would I haven't bothered to draw any actual numbers because I just want the visual sense to be clear. You would start at some corner, and then you would move to a better corner, and you'd move to a better corner, and a better corner, and a better one, until maybe at this point you find that you're better than all your neighbors, or you're at least as good as all your neighbors, and then you put your pencil down and say, okay, I'm done. So that is geometrically, visually, that is what the simplex method is. That's how linear programs were solved up until the early 1990s. And I should say, actually, people still solve linear programs using this approach all the time. It's not the cutting edge, fastest, best way of doing things, but it is a very powerful method. And you've now seen visually all there is to it. And the remaining stuff that we're going to talk about is just how do you do this with numbers? How do you do it without looking at, polyhedra and 900 dimensions or whatever it is? Now, the last little piece of this before we actually get into the method is that we have to talk about corners in the context of standard form. It turns out, all right, people didn't know this when they invented the method. It was one of the major insights the key insights that led to the development of the algorithm was that it actually helps things. It helps to speed up your process if, instead of looking at constraints with a bunch of inequalities, which we've just been doing this whole time, it turns out that standard form actually is easier to work with. Okay, now what is standard form, or how does that differ from the way we've been attacking things in this lecture so far? Well, standard form, remember, you have to have all of your constraints with equal signs. And we've explicitly done the opposite of this, right? We've said all of the constraints have to have inequality signs in them. And then we defined corners by looking at sets of constraints and solving them, right? Where a standard form is expressly the opposite of this. All of the constraints have to have equal signs in them, and it's the variables that have the inequality. And so you could say, all right, now this is different, right? I don't know how to deal with corners in this case because the definition that you've been provided doesn't apply here. It's not a big change. It looks like this. We'll do it by way of example. So here we'll start with a polyhedron here. This is not standard form. This is the inequality form for constraints because these linear constraints here all have inequalities. We'll start with that. And the corners, you could work that out using everything that we've done so far. The corners it has 4 of them. It's a quadrilateral. If I write this, if I then do the tricks that we learned for converting a non-standard form problem into standard form, you could insert 2 slack variables and get this standard form set of constraints here, right? This says you have equal signs now for the constraints, and then all the variables are non-negative. And the corners end up being these things down here. Now, these corners, I should say, they're the same corners as these up there. You have 4 for each of them. But you have, you've introduced slack variables, so there's 2 other quantities that you don't care about. But they're the same corners, and you can verify that by observing, I'll erase some stuff here, by observing that the first 2 entries, the x1 and the x2s, are the same, right? You've got 0, 0, and a 0, 0, and a 0, 3/4, and a 0, 3/4, and a 7/5, 2/5, and a 5/3, comma 0, right? So the actual corners have not changed. So I've just done that, and so let's try and recover. All right, how do I talk about corners in the context of this new standard form problem here, which has 4 variables in it? So it's not a big change. It's the same kind of enumeration that goes on. But what you do now is instead of looking at sets of constraints, you now look at sets of variables. Okay, so as before, we'll say M is the number of constraints and N is the number of variables. So you have an M by N matrix here that gives you your linear equality constraints. And now what you do is you look at every set of variables of size M. And for each such set of variables, which we call B, which stands for a basic set because it forms a basis, you do the following. And again, we'll work through examples of this, which I think are a lot clearer than me describing this in words, but I just want to state this now for posterity. What you do is you build a square matrix by taking the M columns of your constraint matrix that correspond to this basic set, and we call that matrix A sub B, okay, A subscript B. And then you solve the resulting system of equations that you get from that square matrix, or by doing Gaussian elimination on that square matrix. And then you just look at your solution and you ask, is it non-negative? If the entries of your solution are non-negative, then you found a corner. And if you have any negative solutions at all, or any negative entries at all, you do not have a corner. So let's work through an example of this. We'll do this one now. Ax is equal to b. X is non-negative. With this is a here. So this is I'll write down what this system corresponds to. I'll do it here. So I've got 5 and 5, 6, 7, 5, and I've got I cannot see 4, 6, 9, 8. And I have 17 and 16 over here. So this is the system equation: 5x1 plus 6x2 plus 7x3 plus 5x4 is equal to 17. And then I got 4x1 plus 6x2 plus 9x3 plus 8x4 is equal to 16. Okay, and then we've got non-negativity, right? X1 through X4 are non-negative. Okay, so remember how when we had in the previous problem where you had a bunch of inequality constraints, you looked at sets of constraints, right? I looked at constraints 1, 2, and 3, and then I did 1, 2, and 4, and 1, 2, and 5, and so on and so forth. Now, when you have equal signs in your constraints, as I do here, instead you look at sets of variables. Okay, so before where you looked at sets of constraints, you looked at rows, you picked out sets of rows at a time. Now you're picking out sets of columns. Okay, and I would look at this system and I would say, well, I've got 4 columns and I've got 2 rows in A, right? 1, 2, 3, 4 columns and 2 rows. Okay, so you'd say how many columns am I going to extract at a time? The answer is you're going to extract 2. You're going to extract 2 columns from this matrix because you have 2 rows. You're going to have 2 columns and you have 2 rows, and so you're going to extract 2 columns because you want a square matrix that you can solve and give you a solution. So what do I mean by this? I mean that you would say if your basic set, for example, is 1, 2, then you would look at the first constraint or the first variable and the second variable, and you would solve the system of equations. You would just isolate. Actually, here, I can just word and doodle on my slides here. You would just isolate column 1 and column 2, and you'd get 5, 6, 4, 6, as I did over here, and you would solve for x1 and x2 here and get 17 and 16. Okay, so therefore, what can I say? I'd say I solve this system here. This is what happens when I isolate things just for x1 and x2. And I solve the system and I get x1 equals 1, x2 equals 2. And what about x3 and x4? Just set them to 0, right? I just ignore them. I've said I'm only looking at columns 1 and 2, so you set x3 and x4 to 0, and you would set x1 to 1 and x2 to 2. And if you look back at the steps in my process, after you solve for those variables, you just ask the question of whether the entries are non-negative. And in this case, they are, which therefore means you have a corner. Okay, let's try another example here. So this is that was how I determined that 1, 2, that the first and second variables gave me a corner. And if I were to do instead the second and third variables, let me erase some stuff here so we can see where we're going with this. I said, okay, 1, 2, yes, that's a corner, and the corner is this thing over here, 1, 2, 0, 0. How about if I did 2 and 3? If I did 2 and 3, that would mean look at the second column and the third column and solve for x2 and x3. If I isolate the second and third column, as I've done down here, and you solve for that system, I'd get x2 is equal to 3.42, x3 is minus 0.5. There's a negative number in there, therefore you are not a corner. So x2 and x3 is not a corner. So you apply this process just as I've done. You look at every pair of variables as I've done when I built this table. I have x1, x2, x1, x3, x1, x4, x2, x3, x2, x4, x3, x4, and I have the solutions here, and then a yes or no whether I have a corner or not. And the whether or not you're a corner just depends on whether there's a negative number that appears anywhere. So any one single negative number, the existence of any one single negative number tells you you do not have a corner. Here's a larger example, which you're welcome to work through if you like. This is three constraints with 5 variables, so 35. Or excuse me, 10 possible corners to look at. And what I did here is I actually just wrote down the actual valid corners, which is these 5 here. So you're welcome to run through these steps and verify that I'm telling the truth, that these are the 5 corners that you actually have to contend with. Here's some code for computing corners in MATLAB using standard form.